Welcome to the new era of video creation with Bowsiate. Today, we will discuss what strategies would you use to mitigate model bias in an AI system? What strategies would you use to mitigate model bias in an AI system, and how would you evaluate its effectiveness? Bias in AI systems refers to the tendency of a model to make decisions that favor certain groups or outcomes over others in a systematic and unfair way. This bias can arise from various sources, such as biased training data, inherent flaws in the algorithmic design, or even unconscious human decisions during the development and data collection process. In the context of machine learning and AI models, it's essential to understand that bias can be inherited from historical data, leading to unfair outcomes in predictions and decisions. The presence of bias in AI models is a significant issue, as it can lead to discrimination or unequal treatment, especially in high-stakes applications like hiring, lending, healthcare, or law enforcement. Therefore, it is crucial to not only identify and understand the different types of bias, but also to implement strategies that can mitigate its harmful effects. Bias can be categorized into several types, with data bias being one of the most common sources. This occurs when the training data is unrepresentative of the real-world population or reflects historical biases. For instance, training an AI model for hiring decisions on data from an industry with gender disparities will likely result in biased hiring recommendations. Algorithmic bias can also occur if the underlying model is designed or trained in a way that favors certain groups. For example, an algorithm that is too sensitive to specific features, such as age or race, might inadvertently lead to biased predictions. Sample bias occurs when the training data is skewed towards a particular subset of the population, leading to the model not generalizing well to the entire population. Label bias arises when human labelers introduce inconsistencies or inaccuracies in the training data, which can propagate into model behavior. Before addressing model bias, it's important to identify and quantify its presence. Bias audits are systematic checks where models are analyzed for fairness across different groups. This can involve examining how the model performs on subgroups based on sensitive attributes such as gender, race, or age. Disparate impact analysis measures whether the model disproportionately impacts certain groups. For example, if a hiring algorithm favors one gender over another, this can be a sign of bias. Statistical parity ensures that outcomes are equally distributed across groups. Models should not disproportionately favor one group over another unless there is a legitimate reason for doing so. Different fairness metrics like accuracy, equal opportunity, and demographic parity are used to evaluate whether the model's predictions are equitable. Accuracy checks if all groups have similar error rates, while equal opportunity looks at whether different groups have the same chances for positive outcomes. One of the first steps in mitigating model bias is through pre-processing the data. Data augmentation techniques can introduce more diverse examples, which may help balance underrepresented groups. For example, if a dataset for facial recognition has limited representation of ethnic minorities, augmenting the dataset with additional images from these groups can help create a more equitable model. Reweighting data is another technique that adjusts the importance of underrepresented groups during training. For example, if certain ethnicities are underrepresented in the data, their data points can be given more weight in the loss function to compensate. Additionally, debiasing techniques can be applied to either remove sensitive features, like race or gender, that could lead to discrimination or to enforce fairness constraints during training. Using synthetic data is another approach, where artificial data is generated to fill gaps in the representation of certain groups, ensuring that no group is underrepresented during training. In addition to pre-processing, algorithmic adjustments can be employed to mitigate bias. Fairness constraints can be added to the model's loss function to penalize the model for making biased predictions. This ensures that fairness becomes part of the optimization process alongside traditional accuracy metrics. Adversarial debiasing involves training a model to minimize bias by introducing adversarial networks that try to identify and correct any bias in the model's decision-making process. This approach encourages the model to focus on features that are predictive of the target variable without relying on sensitive features. Regularization techniques can also penalize the model for biased outcomes. This helps to constrain the model's learned representations, ensuring they do not disproportionately benefit or harm any group. Finally, multi-objective optimization allows the model to simultaneously optimize for both performance, e.g. accuracy, and fairness, ensuring that fairness considerations do not come at the cost of model effectiveness. After training, post-processing techniques can be used to further mitigate bias. Re-ranking predictions ensures that the model's outputs meet fairness requirements. For instance, if a loan application model is biased toward one gender, the predicted outcome can be adjusted to ensure fairness after the prediction is made. Equalized odds ensures that both false positive and false negative rates are equal across different demographic groups. For example, in predictive policing, it is important that the model does not disproportionately assign higher risk scores to specific ethnic groups. Thresholding involves adjusting decision thresholds for different groups to ensure equal treatment. If one group is less likely to be accepted by the model, you can lower the decision threshold for that group to compensate for the bias. Fairness through awareness is an approach where the model output is adjusted according to predefined fairness criteria after the prediction is made, ensuring that fairness goals are met. Bias mitigation doesn't stop after the model is deployed. Continuous monitoring is necessary to ensure that the model's predictions remain fair over time. Regular fairness audits can identify any new bias that may have emerged after deployment due to changes in data or the environment. Real-time feedback mechanisms can help incorporate user feedback and real-world data into the model to adjust and improve fairness. It's important to monitor for bias drift, which refers to the model's performance becoming more biased over time as data distribution changes. Finally, A/B testing different versions of the model, biased versus unbiased, can provide valuable insights into whether the model's bias mitigation strategies are working as intended, allowing teams to iteratively improve the model. Evaluating the effectiveness of bias mitigation strategies involves using both performance metrics, like accuracy, precision, and recall, as well as fairness metrics. While ensuring the model's predictions are accurate, we also need to ensure that fairness metrics like statistical parity or equal opportunity are met. Incorporating stakeholder feedback is crucial, especially from groups who may be most affected by model predictions. It's essential to include a diverse range of perspectives in the evaluation process to ensure that the model doesn't inadvertently harm any particular group. Ethical auditing involves a thorough evaluation of the ethical impact of the model's predictions, ensuring that they align with the values of fairness and justice. Comparing the model against established model fairness benchmarks also helps in assessing whether it meets the industry standards for fairness. To summarize, mitigating model bias involves a comprehensive approach across several stages. In the pre-processing phase, data augmentation, reweighting, and debiasing techniques can ensure that the training data is as balanced as possible. Algorithmic adjustments like fairness constraints and adversarial debiasing can address bias during model training. In the post-processing phase, techniques like re-ranking and thresholding can be employed to ensure that the final model predictions meet fairness criteria. Finally, continuous monitoring ensures that the model remains fair over time through regular audits, real-time feedback, and the identification of any bias drift. In conclusion, mitigating bias in AI models is essential for ensuring that AI systems are ethical and serve all stakeholders equitably. This process requires a comprehensive approach, combining pre-processing, algorithmic adjustments, post-processing, and continuous monitoring. It is not a one-time fix, but an ongoing process that demands vigilance and iteration to ensure the model remains fair and unbiased throughout its lifecycle. By addressing bias early and continuously evaluating and improving the model, we can move towards building fair AI systems that are not only effective, but also just and transparent, ultimately benefiting society at large.